So I'm a chemist. I work at IBM Almaden Research Center, and I work in polymer synthesis, which means that I make plastics. When I talk to most people about plastics, these are the kinds of images that come up, right? So we think about plastics as pollutants, as materials that are harmful to our environment. Birds eat small pieces of plastics and have them in their stomachs for a lifetime. The Great Pacific Garbage Patch is a huge area in the Pacific Ocean that is mainly comprised of small pieces of plastic just floating around. It's been estimated that it's over the size of Texas, but we can't even predict that because it's everywhere. We also think of landfills. So plastics and materials ending up in landfills. Plastics take a very long time to biodegrade. So it's estimated that they take between 500 and 1,000 years to biodegrade. And if you think about plastics, they're only about 100 years old. And so that means that the first plastics ever invented still exist on this planet. In addition to that, we do some recycling, right? So most of the things that we do recycle have to have something in common, which is that they can be melted down and remolded. This makes it really cheap to recycle them, but it also limits how many plastics we can actually recycle, because it turns out that not all plastics melt. So one particular area of plastics, or class of plastics that don't melt, are our thermosetting materials. And thermosets actually represent a class of some of the world's strongest polymers. And they're already used in things like airplane parts, for example. So in the tail of the Boeing 787, that's an example of where we use a thermosetting material as a composite. But even in that case, most of our materials after a lifetime end up sitting as some sort of waste. So I'm going to tell you a story. So I'm, as I said, a synthesis person, and one day I was in the lab working on a reaction that I was setting up from broken down PET. So PET is the material that the water bottles on your tables are made out of. So we were literally cutting them down into pieces, breaking them apart, and then using that as starting components to make new polymers. I added a couple ingredients together, and I stepped away from the flask to gather a third. I came back, and by the time I had returned, the flask had completely solidified, and I wasn't really expecting this. I tried to get the material out. I couldn't get it out. I had to break the flask with a hammer in order to get out the material to figure out what I had made. Some of the starting materials that we put in the flask that day are similar to the world's first polymers, so they're not unknown to the polymer community, but this plastic seemed to behave very differently. And I'll tell you why, because this is actually going to be a part of the solution. This is the reaction, and although I don't expect you to understand all of the details of it, it seems very straightforward. You put two things together, and then you form, in this case, a solidified object. So the first solidified object that I actually found in my flask that day is the red structure here. This structure is interesting because you can actually still react it, even as a hard chunk of material. So if you take the middle structure and then heat it up even further, then you get the structure on the far right. So we thought this was really interesting just from a very fundamental scientific standpoint. And I wanted to understand a little bit more about why some of these materials remained reactive and if I could actually use that reactivity to our benefit. So I turned to my computational colleague, and he helped me calculate the reaction profile. And this, as you can imagine, and as you can actually see, is a very time-consuming process to calculate all of the different steps of the reaction. You can think of this as this reaction coordinate diagram as being like on a timeline. So on the left, you have the starting materials. On the right, you have the products. And as you can see, it's a downhill slope. And what that means is that it's energetically favorable. So a couple of things stood out on this plot. One was that there was actually two very stable structures. They're highlighted in red. And it made sense then that what we were doing was accessing the first structure in red on the left. And when we applied heat, we were actually causing another transformation, and it would go to the structure on the right. And some models of these are shown here, just to give you a sense of what this chemistry actually looks like. It turns out that through studying the actual mechanism, we could figure out that this reaction was very sensitive to things like the environment that we ran the chemistry in, as well as things like electronics and like where the electron density is distributed over the monomers. And furthermore, we could figure out how it would change if we added things like, say, proton source, otherwise known as acid, so how it responds to pH. The other critical thing about figuring out the reaction mechanism is once you figure out how you can go forward, you also can figure out how to go back, since we know the direct pathway. So I'm going to show you a video. I'm going to show two different polymers. One is a commercial polymer that's commonly used. One is the thermosetting polymer that I showed in the slide before. I'm going to put them into a vial with dilute sulfuric acid. And what you see is that the polymer, the commercial polymer, is that disc, and it floats, it sinks down to the bottom, whereas the polymer that I've been talking about, the thermoset, actually floats. After 12 hours, the thermoset completely dissolves, whereas the commercial polymer is completely unaffected. You can then neutralize the pH, and you can see it kind of clouds up. That cloudiness is actually the monomer form of my polymer. In other words, it's the starting material, the very fundamental unit of my polymer. You can then filter it simply, and then collect it. And once you have it in hand, then that monomer can be reused again to either make this polymer again, break it back down, and have this sort of loop, or you could use it to build another polymer of choice if you wanted to target something with particular properties. And so what you maybe don't necessarily realize by watching this video is that the polymer on the left is actually stronger than bone when we do measurements on it. And it can be broken back down to a powder. That's not very common. And as I already said, usually when we think about recyclable plastics, they have to be melted and in order to be recycled. This is a new way of recycling that doesn't require melting. In addition to that, because once again, we've studied the chemistry and understand the chemistry very well, we could figure out how to make other materials that had different types of properties, but still had this ability to revert. So I already mentioned one that's stronger than bone, but if we swap out the monomer for a more flexible monomer that is a larger molecular weight, we could actually make these gels. And you can see that there's blue and white segments in these gels. The reason why it's blue and white is that we actually started with this one piece with two pieces. One was blue gel, one was a white gel. If you take each of them and cut them in half and then put them together in alternating sequence, they seamlessly reheal into one cohesive piece. We call this self-healing. So this is actually an example of a self-healing gel that, as you can tell by the picture, is actually extremely elastomeric and stretchy. And to boot, that's about 90% liquid. And you can see that it's all contained within the structure. So this is a very interesting twist. And once again, all of these materials can be reverted, starting from a pile of powder, also known as the monomer starting material, polymerize it into the plastic, dilute it, sulfuric acid treatment, it goes back to the powder. So what can we do with this? There's been a lot of advances recently in things like portable additive manufacturing technologies, also known as 3D printing. We also have come great leaps forward in computational chemistry, and an example of that I think I showed you earlier. If we combine these two advances in technologies, you can think about the opportunity to design materials that are actually designed to be broken down or to be recycled. So you put in some sort of functionality that you can trigger with a stimulus such as pH or UV light or whatever you want and have it break back down to its starting components. Because you have the ability to build polymers on site and parts on site with 3D printing, you can envision places that have limited resources, right? You take your part, you break it down, and then you can build it back up again with your 3D printer. Some places that have limited resources, for example, are places like space. So think about it that way. The other thing that's really great about that is that you can use your resources all stay in one spot, so you never have to transport them from place to place. Once you've built your part, you have your resources in hand and then can just rebuild. So I think this is we're going to start seeing a lot of changes in recycling. We're going to start seeing a lot of changes in manufacturing of plastics, and our relationship with plastics, I believe, are going to start changing. We need to change our relationship with plastics. We are not going to live in a world without plastics. So we need to figure out how to make it work for us and have it be a sustainable resource. As a scientist, I dream of discoveries that will change the world. It is my hope that this new material makes its mark, not only by changing our negative view of plastics, but by reintroducing them as affordable, diverse, and sustainable materials that will someday comprise many of our everyday products. Thank you.